So good afternoon, everyone. And first, I would like to thank the organizers for providing me this opportunity to present my work here. And today I will talk about hidden superuniversality in systems with continuous variation of the critical exponents. So this is based on our recent work with Professor P.K. Mohanty. So what we know that the phase transition and the critical behavior have been emergent topic of research in statistical mechanics over several decades. And the criticality is associated with two basic features. So one is the universality that states that the critical exponents are universal up to symmetries and certain spatial dimensionality, and another is the scaling function. Now, in this region of statistical mechanics, one of the most celebrated models where the critical behavior has been studied exactly is the Ising model in 2 dimensions. So though it's a well-known model, but I am just briefly describing. So this is a periodic 2-dimensional square lattice, and at each side, the site may be occupied by either a upspin or downspin, and the spins they interact with this following Hamiltonian, where this J is the interaction strength. And for this Ising model, the critical behavior has been exactly studied, and these are the list of critical exponents, and these critical exponents, they follow these scaling relations. So for today's discussion, we are interested about this type of 2-layer Ising system. So each layer is a periodic square lattice, and we consider that each side of these 2 different layers, so there are 2 different kinds of Ising spin. For the upper layer, we call it a sigma, and for lower layer, we call it as tau. So sigma and tau, maybe both of them may be either +1 or -1. And these spins, they interact with this following Hamiltonian, where this J sigma and J tau are the interspin interaction strength for the spin sigma and tau respectively. And this parameter lambda, it represents the interaction strength for the 4-spin coupling. So this model is commonly known as the STATISTICAL model, of which the critical behavior we want to concentrate on in today's presentation. And to start with the critical behavior, we first need to define what are the order parameters for this system. So from this Hamiltonian, we see that this Hamiltonian remains invariant under this symmetry transformation of this sigma and tau spin. Thus, one can safely use as an order parameter either this sigma average or tau average, that is a magnetization, and we also use for the Ising system, or this sigma tau average that we can also use as an order parameter, which is known as a polarization for the electric transition. So first we review the phase diagram of this STATISTICAL model in this lambda j plane, where we consider this j sigma equal to j tau equal to j, and this is the phase diagram. This red line, this xz4 line, is the critical line at temperature T equal to 1, which can be obtained from this self-dual condition. This self-dual condition basically, it relates the 2 interaction parameter lambda and j, and this critical line, it separates the 2 regions. One is the ferromagnetic, where magnetization, polarization both are ordered. This is the paramagnetic, where magnetization and polarization both are disordered, and there are other 2 phases. For phase 3, the magnetization is disordered, but the polarization is ordered, and phase 4 is similar to phase 3, but the polarization is ordered antiferromagnetically. So these are the 4 different phases of this STATISTICAL model. Now, if we see just this Hamiltonian, we will see that there are 4 different limits of this interaction spin lambda and j, for which the Hamiltonian reduces to 2 well-known models. So first, for lambda equal to 0, lambda equal to 0 means that the sigma and tau spin, they are basically decoupled, and we can write this Hamiltonian as a 2 independent Ising Hamiltonian with the critical interaction strength Ji, which is marked in this point. And for lambda equal to j, this Hamiltonian remain invariant under this permutation of the 4 spin sigma and tau. So it's like the 4-state Potts model with the critical interaction string Jp, which is marked in this point. So what it means that if we study the critical behavior in lambda equal to 0 point, so it will be Ising-like, and for lambda equal to j point, it will be Potts-like. Thus, the question that remains relevant, that if we study the critical behavior on any other point along the critical line, so will it be Ising-like, will it be Potts-like, or will it be some other different? So that's the question that bothers us. Now, for this STATISTICAL model, the critical exponents have been exactly derived by Baxter, and we have also performed the Monte Carlo simulation to obtain the critical exponent for both the magnetic and electric case. And what we see that for magnetic, with these different lambda values, the critical exponent, they differ, but their ratios remain invariant. So it means that the magnetic exponent, they obeys the weak universality scenario, whereas for the electric case, we see the exponent and their ratios, so all of them, they basically varies with this parameter lambda. So this is the most generalized continuous variation of the critical exponent along this critical line. So what we have discussed till for that along the critical line, the critical exponent, they changes continuously, and what we look for, that is there any other features that remain invariant along the critical line. So the natural choice is to look for is the finite phase scaling, and for the order parameter, both magnetization and the polarization, where it exhibits this finite phase scaling, where this delta T is the deviation from the critical temperature. And following the Monte Carlo, once we plot this scaling function of the order parameter, we see that for different lambda values, the data for different system sizes, they collapse onto a unique single one, and for different lambdas, these scaling functions are different. But the point which is interesting is that if we just rescale this x and y axis, up to a certain multiplicative factor, we see that these different scaling functions, that they could be collapsed onto a unique single curve of onto lambda equal to 0. So the red line is for lambda equal to 0 and the other symbols are for different lambdas, so they may be collapsed onto a unique single one. The similar scenario we can see for polarization and also the other scaling function of the order parameter for in the presence of field. So B is the field conjugate. Here also both the magnetization and polarization. So in all the cases, what we see that though the critical exponents are different for different lambdas, but the scaling functions are the one quantity that is universal up to certain multiplicative factor on the critical line. So now what we look for, so is there any other quantity that remain invariant where if we study the critical behavior and the different lambdas for the data for different lambdas and different system sizes, they naturally collapse onto a unique single curve without rescaling the axis. So that we look for. So first we study the Binder cumulant, which is the RG invariant quantity, and the Binder cumulant can be defined for the magnetic and electric transition by these two forms, and it also follows the scaling relations. So now following the Monte Carlo, once we plot the scaling functions of the Binder cumulant, we see that without any rescaling, these data for different system sizes and different lambdas, they naturally collapse into a unique single curve. Another RG invariant quantity that gives or helps to provide a more universal check, more permanent check, is the second moment of correlation length, Xi2. So Xi2 that we can define from this correlation function, and from Monte Carlo we again calculate this second moment of correlation length. What is that? This deep? Okay, so that basically that we can that we have not checked. That is a function that we got, but we have not investigated what is that. Yeah, that's it. Yeah. So what we got that again the Binder cumulant versus this Xi2 plot, that both the RG invariant quantity. Here again for different system sizes and different lambdas, all the curves they collapse onto a unique single curve. So what we can see that for all the cases, all the cases that I have discussed, this good scaling collapse basically indicates the existence of an underlying universal scaling function along the critical line. So what we can say that though there is a continuous variation of the critical exponents, that the scaling functions along the critical line, they must be identical to that of the base universality class, and we proposed it as a super universality hypothesis. We have also found a generic functional form of the variation of the critical exponents, but that part I am not going to details. And we have also compared it with the variation of the critical exponents with the parameter lambda from Monte Carlo simulations. And what we can say that this variation from the Monte Carlo simulation, they match very well with the exact functional form of our exact analysis. So at last, what you can say that this super universality hypothesis is basically is very much helpful to identify that whether two sets of critical exponents that can be obtained from the numerical data or the experimental analysis, and if these two sets of critical exponents they satisfy the hyperscaling relations, so whether they belong to two different universality classes or they are the instances of the same universality classes generated by a marginal parameter for our case, which is lambda. So this is a summary of my today's presentation. So we know that renormalization group allows continuous variation of the critical exponents along the marginal direction, and we study it for the Askin-Taylor model, which is ideal laboratory to test that because there is a continuous variation of the critical exponent for both the magnetic and electric. And we have studied that. We proposed a super universality hypothesis for the scaling functions along the critical line must be identical to that of the base universality class, even though there is a continuous variation of the critical exponents. And these invariant scaling functions carry forward the universal features of the parent universality class. So I would like to acknowledge my supervisor, Professor P.K. Mohanty, with whom I have done this work, and my funding agency, CSR. So thank you.
No time for quick questions.
Yeah.
RG allows continuous variation of critical exponent along a marginal direction.
Yes.
How you know it?
Because that we have also seen here. For here, the marginal parameter is lambda, and we see that that for the Askin-Taylor model from the exact critical exponent and also from our Monte Carlo analysis, that the critical exponent for different lambdas are different. So they vary continuously along this line.
Yeah. Have you any RG equations?
No, that we have not done.
Then?
No, but there is this, what I can say.
Have you done anything in your life on the critical exponent analysis from the perspective of quantum field theory?
No, that we have not done.
You know what strong conjecture, what strong conclusion you have done here. Those
no, but there is a paper by...
Those who are doing the quantum field theory RG, we know. Those who are doing the quantum field theory RG, we know. what you are.
But
Okay.
there is a paper by Bonatti and in physical review later. So they have done this field theory argument and they followed that with the marginal direction, this critical exponent vary.
Okay, if there is no more question.